So we're going to start proofs today with looking at algebraic reasoning. And let's talk about things that we already know that we can start using in our proofs. So we can use properties, theorems. Let's write that a little neater. Postulates and definitions in our proofs to justify our steps. And theorems, this word we haven't really been using, but it's ideas that we can actually prove. So there might be times where I'm asking you to prove a theorem, and in that case you want to make sure you don't use a theorem to prove itself. So we want to say things like a writing instrument is a pencil because it just is a pencil. You want to be able to describe it, you want to be able to give me more details. So we'll get to that later on when I'm asking to prove theorems, but it's just something to keep in mind, that you can prove all theorems and we don't want to use a theorem to prove itself. Okay, let's just recall some things that you already know. So let's talk about some definitions and some postulates and theorems. So I want you to see that we've actually already gone over a lot of things that you can use in your proofs. So for example, we talked about the definition of midpoint, the definition of a bisector, the definition of supplementary angles, complementary angles, we've also seen straight angle and right angle. And one that a lot of people forget we can use is the definition of congruence. So if you've forgotten what any of these words mean, you can feel free to go through and look at your notes or look at the glossary. But those are a lot of words that we might be seeing in terms of information that you're given or things we can use to create, links in our proofs. All right, postulates and theorems. So some that you might remember are segment addition postulate, the angle addition postulate, and there's some theorems and postulates that don't really have these like nice and pretty names. For example, you know that any 2 points create a line, and any 3 points, 3 non-collinear points actually, create a plane. Two lines intersect at exactly 1 point. And related to that, 2 planes intersect at 1 line. One we talked about that we haven't really been using before is the vertical angles theorem. Remember, that means vertical angles are congruent. And also one that we probably know but we haven't seen named is the linear pair theorem, saying if we have a linear pair then they are supplementary. All right, so we're going to ease into proofs today with looking at algebraic proofs, and to do that we're going to look at properties. So
what we're going to do is we're going to look at these different properties of equality, properties of congruence, and we are going to do some basic proofs. So properties of equality, you probably remember from Algebra 1, the addition property of equality. So it basically is just what we've been using when we solve equations. So for example, if we have something for any real number, let's say x, which is equal to y, if you take x and you add a number to x, for example, x plus a, then that is going to equal y plus a. So you keep the equation balanced. Right, so that's your addition property of equality. Subtraction property of equality, same idea. Again, if you have two numbers that are equal to each other in an equation like this, x equals y, and a real number x and y, if you take x and subtract a number from it, for example, some number a, then to maintain that balance, we need to make sure we take that a away from y as well. So that's your subtraction property of equality. Okay? So you can imagine the next couple below, same idea, multiplication property of equality and division property of equality, just what you've been using back in Algebra 1 to solve your equation. So same deal here. If x is equal to y, then if we take x and multiply it by some value a, to keep it balanced, to keep the equation the same, we have to take y and multiply it by a as well, right? Lastly, if x is equal to y, then if I take x and divide it by some number, whatever I do to one side, I do to the other to make sure that the equation is balanced and the values are not changing, so they're still equal. Okay, so those are your basic four properties of equality that you've been using a lot, right? We just may not have known the vocabulary to go with it. The next one is the reflexive property of equality. So the reflexive property of equality is just basically something is equal itself. X is equal to X, or 1 is equal to 1, right? Just saying that it's equal to itself. And this one, you'll see where it's used later on when we do some proofs, but you want to be able to recognize it and give me an example if I ask you for that reflexive property for now. So know that vocabulary, okay? Symmetric property of equality. This one I think is a little easier to remember. It's basically because it's symmetrical. So it's basically saying if x is equal to y, then y is equal to x. So you can change around that order with that equal sign and it won't change the meaning of the equation, right? So if 2 is equal to 3, or excuse me, 2 is equal to x, then x is equal to 2. That's basically it, okay? Transitive property of equality, it's kind of like that law of syllogism. It basically links things together. So we would know, for some example, if A is equal to B and B is equal to C, we can basically cut out those B's in the middle and say, then A is equal to C, right? So again, kind of like if X is equal to 1 and 1 is equal to Y, then we can say x is equal to y. So that's your transitive property. So you have some linking piece of information that we cut out and we just put the two ends together, so A and C. All right. Substitution, you've been using this probably for years. So that's just basically saying same thing, right? For example, if x is equal to 3, then 3x is equal to 3 times 3, right? So you're basically taking that value and plugging it in. So oftentimes you can actually do two substitutions to do transitive property. If you don't remember transitive property, just stick with substitution. All right, so those are our properties of equality. Some of those same properties work with congruence. The only difference now is we're looking at the congruence symbol. So the reflexive property of congruence, Now, instead of looking at numbers, remember when we're talking about congruence, we're talking about like an image, right? So we're thinking a figure. Okay, so if we look at the reflexive property of congruence, we saw the reflexive property of equality earlier saying, like, for example, 1 equals 1, right? You equal yourself. Now we're saying in our congruence property, for example, the segment AB, that's going to be the same size and shape as itself, segment AB. So we're not looking at numbers here, but we're saying I could overlap this segment and it would match on itself completely. Okay? Symmetric property of congruence, same idea here, but again, we're looking at a figure. So I could say, for example, segment AB, let's say that's the exact same size and shape, it's congruent to segment XY, right? The symmetric property of congruence says we can change that order and it won't change the meaning, right? So I could write XY as congruent to segment AB. That means, again, if we look at their shapes and transform them, move them around, they're going to overlap and match up perfectly. Okay? Transitive property of congruence, same idea. So remember, we don't have to be limited to segments. I could, for example, say angle 1 is congruent to angle 2, right? So if angle 1 is congruent to angle 2, and angle 2 is congruent to angle 3. So again, meaning they have the exact same size and shape. If you imagine drawing it, you could overlap them and they'd match up perfectly in the angle size. So if I know angle 1 is congruent to angle 2 and also angle 2 is congruent to angle 3, then remember, cut out that middleman and we can say angle 1 is congruent to angle 3. All right? So same idea really in the sequence and the pattern as the properties of equality, but the only difference here is the meaning behind the notation. So we're looking at the figures. All right? So be careful with your notation.